we are going to explain the third part of the Pintos project. We're going to implement virtual memory. Probably this is the most interesting and most funniest project among the 4 projects in Pintos. This is the relationship between virtual address space and physical address space. A process has its own process address space, and there is a physical memory. And Pintos memory have stack and initialized global data and text. So this is the layout of Pintos virtual address space. As you can see here, Pintos does not have a heap. So Pintos does not have a heap in its address space in current implementation. And there exists a page table. Page table structure is defined by hardware, and Pintos relies on x86 architecture. So in reality, Pintos has a 2-level paging, which consists of page directory and page table pages. And then it maps for each virtual page into the physical page. So there are one red block that represents a stack, and there is one orange that represent an initialized data, and there are 2 blocks for initialized data, and there is 1 block for represent a test. So page table contains an information about the location of individual virtual page. And then if you look at actually among these pages, initialized data, which belongs to the file, and also text is mapped from the file. So these 3 blocks, first, second, and third, actually has its matching location on the disk. In current Pintos, when the process starts, the entire executable file is loaded at once at the beginning, which is pretty much inefficient because not all part of the file is executed. And so the physical addresses of individual page is fixed at the beginning of exec. So with this characteristic, this is pretty inefficient. So we need to implement the real virtual address. In real virtual address space implementation, we have to basically do 4 things. First, we need to enable demand paging and swapping. And then, second, we enable the stack growth. In current Pintos process structure, each process is allocated 1 page of stack. And if a stack runs out of space, then program dies. But now we are going to enable the stack growth. The third one is the memory file. In this project, we are going to implement memory mapped file. So we are going to implement mmap and unmap. From the physical pages point of view, there are 2 types of physical page. One that has matching disk location, and the other one that does not have matching disk location. Let me go back to the previous page. Here, there are 5 pages in total. 1, 2, 3, 4, and 5. Out of these 5 pages, page 1 and page 2, it does not have matching disk location. And page 3, 4, and 5, these 3 pages have its own matching disk location. So these 2 pages is called anonymous page. And these 3 pages are called file back page. And then the third, fourth step, we are going to implement enable accessing the user memory. So now let's start. Let's review the four basic concepts we have just covered in the previous class. There are virtual page, and there are page frame, and there are page table, and then there's swap space. So virtual page consists of 32-bit address space. This is virtual page. And virtual page has 20-bit virtual page number and 12 bits of offset. So this is 20 bits and this is 12 bits. And Pintos has an array of physical page frame, and each frame has a number. So page frame consists of page frame number and its offset. So the role of page table, there is a page table, and it contains 2 to the 20 page frame numbers. And in x86, page table consists of two-level paging. In reality, it consists of two-level paging. There is a page directory, and then there is page table. So this is page directory, and this is page table page. And then not all virtual pages are present in memory. So we are going to implement a swap space. Swap space is a part of disk region that can be used as a part of memory. So it can contain, this is physical pages, but it reside at the disk. That's what we call swap space. So swap space is a part of disk region, and it is an array of page side blocks. Let's think about a page in a virtual address space. In virtual memory, we need to load the page from the disk as requested. That's the heart of page from memory concept. Load the page from the disk as requested. We call it a demand paging. So a page in virtual memory can be either in memory only. So this is the important part. In memory only. So it does not have a matching disk location, or it can be a part of file. So this is what we call file back pages. Let's look at the page in virtual memory. If it's a page in the text region, then it'll be part of the file. It's binary file. If it's a page about a data region, then it also is going to be a part of the file of ELF format. For example, ELF. And if a page in BSS section represent an initialized global variables, so it resides only in memory and does not have a matching disk space. Stack and heap is the same. It's in memory only pages. And also there are a region that is mapped to the file. This is, we call it mmapped region, and it is a part of the file. Of course, when we call mmap, you don't want to specify the file descriptor. So then in that case, mmap is used to allocate a memory segment in the virtual address space, but it does not have matching disk space. So mmap can be used to map the file, or without mapping the file, to allocate the virtual memory segment. In current Pintos, there's pagefold function. This pagefold. This function is called when a given page does not exist, and you are required to modify this function. In current Pintos, If page fault occurs, then it kills the process. But if you successfully implement this project number 3, then when page fault is called, your page fault function will search the disk, allocate the page frame, and loads the appropriate page from the disk to the just allocate page frame. That's what you are required to do. And that is going to be very, very interesting. So you will enjoy it. So let's conceptually explain how Pintos handles page fault when you implement the virtual memory. So when page fault occurs, what the Pintos is supposed to do? First, it has to check if the memory reference is valid or not. If it's valid, then it needs to locate the contents, then needs to go into the virtual memory page. So, page fault has occurred. It means that there are two situations. The address itself can be invalid, or the address is valid, but the page somehow is not in memory but in the disk. So if the address is invalid, then you need to kill the process. So that's what is going to happen here. If the address is invalid, then you need to kill the process. Why does it happen? The address may not be the valid user address, or the address is valid, but it may belong to the call address. Or it may be a valid address, but you do not have proper permission to access that page. For example, it is read-only page, but somehow you want to write something, or you try to write something, then the operating system checks the permission and it kills the process that performs invalid operation. So that's what is going to happen when your address access is invalid. Okay, so what if it's valid? Page fault has occurred, address is valid, but it finds that the requested page is not present in memory. Then next thing is you have to locate the content that needs to go into the virtual memory page. And then there are three cases. It may be read from the actual file, or it may be read from the swap space, or it can be simply all zero page. Okay, so in that case, the address is valid, and you have determined the original location of the physical page from the file or from the swap space, or you just simply need to allocate page frame. In that case, you need to allocate a page frame. What do you mean by allocating the page frame? In any computer system, DRAM or physical memory consists of 4 kilobyte pages. We call it a page frame. And some page frame is free, some page frame is used, some page frame is used, and some page frame is free. So when page fault occurs, Pintos operating system needs to scan all the page frames, and then you have to select one and allocate to the user process. That's what we mean by allocate page frame. And then once you select the free page frame, then as a next step, you have to load the appropriate page from the disk to the requested disk, request page from the disk to just allocate page frame. Okay, so once you fetch the data from the disk to the page frame, then you need to update the page table. Then that's the end. Looks simple, right? Okay, then what are we supposed to implement? We have a page table, and that is provided by Pintos and that is provided by actually x86 CPU. This is page table. Page table maps virtual page number to physical page number. Physical frame number. But to implement a virtual memory, we need more information about individual virtual pages. For example, we have to understand what is the disk location of a given virtual page. Or if we have to know whether a given virtual page is file backed or in memory only, those type of functions. So definitely we need an additional set of information for individual virtual page, and we have to define a data structure for individual based virtual page that contains these additional information. So let's examine what kind of extra information we need to specify for individual virtual pages. First one, virtual page number. The second one is the read-write permission. So whether a given page is for read or write. And third one is a type of virtual page. So a type of virtual page represents if it's a page of executable file, and whether a page is part of a general file or a page is from the swap area. So if a page is from a swap area, then it means that page is an anonymous page, which does not have file vector region, which does not have a matching file. And the reason we differentiate the file page that is from the executable file and then general data file is that when you execute the executable file in the previous page, you make it unwritable, unmodifiable. So from the virtual pages point of view, we have to differentiate the page from the executable file and the page from general file. The reason is to prohibit the pages from the executable file from being modified. So we need a field for type of virtual page. And then in case a page is from the file, a page has to carry the information about which file it is from and then the associated offset of the file. So it needs a reference to the file object, which file it's from, and then offset. And also page is 4 kilobyte, but it is true that not all 4096 bytes are full. For example, there's 4K byte, but only 2/3 of the file contain the valid information. Right. 1.3, sorry, for example, 2.6 kilobytes contains valid information. So it usually happens when a page is the last page in a file and file is not aligned with the page size. In that case, the last page does not have proper contents to fill its all. And then also it may contain the location in the swap area. And then it contains in-memory flag to determine is it in memory or not. So for each virtual page, we need an information to represent this information. Okay, so this is big picture of what we need to implement in realizing the virtual memory. Let's define a data structure called VM endbar entry. This is set of attribute that represent the set of information mentioned in the previous slide. It's defined for each page. So when a program tries to access a certain part of memory, we first have to consult a page table and assume that it finds that the given page is not in memory. In that case, the page field occurs. And then first thing it have to do is the page fault will occur, and then it has to allocate one of the free frames from the array of page frame entries. And then it needs to allocate appropriate disk blocks and then load the pages into memory to whatever page frame it is allocated. And then after it just got allocated, it reads the blocks from the disk to memory. The operating system allocates a VM entry data structure and then initialize it. This is skeleton structure of allocating a virtual page object and then read the associated data blocks from the disk to memory. So now this picture looks almost the same except one thing. So let me go back to the previous slide. There is virtual address, and there is physical address, and there is page table. These are three basic entities that forms virtual address space. Let me go back to the page 11. Now I'm going back, sorry. So here, you may find there is one new thing. This is the one. So this is a set of virtual memory entry for a given process address space. Okay, this is the data structure VM entry we have defined in the previous page. And then if there are 5 pages, 1, 2, 3, 4, 5, for example, and then each page has the associated virtual memory entry data structure 1, 2, 3, 4, and 5. So each VME object represents a page in the page table. So this is the one you need to implement. So define the virtual memory entry, and for each process, it maintains a set of virtual memory entry object. You may use linked list, you may use hash table, or you may use an array to represent a set of virtual memory entry for a process. So this is basic entity of implementing virtual memory. Let's look at the details. So this big figure represents a virtual memory address for a process from the implementation's point of view. It contains thread structure, and Pintos thread contains a pointer to the page table. The name of the field is page directory. So page dirs points to the start of the page directory. And then you are going to add a new field here. This is important. The name of the field in this example is VM, but you may want to use whatever name of the string you want to use here. And then this represents a pointer that points to the set of virtual memory entry. Like this. And in this example, we are using a hash table structure to represent a set of virtual memory entries for a process. We are using hash table. And virtual memory entry is organized using the hash table and buckets. Isn't it simple? So in the skeleton Pintos, there is a page table, and there is physical memory, and there is a disk. But the original Pintos does not have a set of virtual memory entries. So this is the part you are going to add. Remember, this is Pintos. This is toy operating system. So we are adding a hash table that contains a VM entry, each of which represent the page table pages. Let's look at the details of implementation of VM on the entry data structure. The name, you may want to choose whatever name you want to choose, but I'm here in this lecture slide. We are using VM on the entry. This is the same name that is used in the Linux data operating system. So we are defining a data structure called VM entry, and we have to fill this out. Okay, and then a single process may have multiple VM entry data structure, and you will have to define a set that can accommodate multiple VM entry objects. So what are we going to use? There are Pintos provide hash table, linked list, or array. In this lecture, we are going to use hash table data structure to represent a set of VM entries for a process. So next, we have to add a field to represent the set of VM entries to the thread structure. So structured thread is a data structure that represents a thread, and this is the thread, and we're going to add a thread data structure, and we are going to add a pointer that represents a set of virtual memory entries, and we are going to use a hash table, the struct hash freedom VM. So this is hash table to manage virtual address space of a thread. And then the next thing you are required to do is when you start a process, you allocate the thread data structure, and then you have to also initialize the hash table you just allocated. So you have to initialize hash table. Of course, because page fault has not occurred, you do not have to allocate any VM entries yet. But you still have to allocate. You have to initialize the hash table. And when process exit, you have to deallocate the VM entries, and you have to also deallocate the hash table. So when a process exits, the operating system deallocates the page table in Pintos. But here you are adding a routine to allocate VM entries for individual pages in the process address space. So when the process exits, you have to add a feature to deallocate VM entries that has been used by the process. So you have to add a function that deletes a VM entry that has been allocated for a given process. So you have to modify exit. In original Pintos, it allocates physical memory by reading all alpha image. It consists of two steps. First one is load segment, and second one is setup stack. In load segment, it reads data and cut segment. In setup stack, it allocates the physical page of a stack. Now, you are going to modify the Pintos address setup initialization process as follows. First, it allocates the page table. At the time of allocating page table, all entries are invalid because it's not bound. Then it allocates VM entry for each page. And important thing, it does not allocate the physical memory at this point. So you have to modify the load segment. And it adds a function that initializes structures related to the virtual address space. It removes loading the binary file to virtual address space. It removes this part. And then it adds the following. First, it allocates the VM entry structure. It initializes the associated field values, and it inserts them to the hash table. This is how it looks like. So this is the original Pintos. So allocating the page, loading the file, and set up the page table. So you remove this part. and then do these things. So create VM entry file initialization, and insert them to the hash table. This is the code. So maybe I am too kind to let you know the details of everything. Here, you have to delete this part. So allocating and mapping the physical page part. So you should remove this part and then add this code. Create the VM entry using malloc and setting VM entry members, and then offset and size of the files to read. And add VM entry to the hash table by insert VME. Okay, so let's look at the process of initializing the stack. At the beginning in the original Pintos, you allocate a single page, and it sets up the page table, and it sets up the ESP pointer. So basically, in original Pintos, a process can have only one page as a stack, and if there runs off the stack, then the process is killed. But now we are changing the process and make the stack expandable. That is very important extension to the Pintos process structure. We need to create VM entry for 4 kilobyte stack page, and then we initialize the created VM entry field, and we insert them the VM hash table. So in setup stack, you add this part. That's very easy, huh? Okay, so you create VM entry for the page you just created for a stack. You are initializing this field. Oops, this is misspelled. This is field. And then you add VM entry to the hash table. So this is, and of how you modify the setup stack function. Okay, this is the function you have to modify here. Then, so next is a big picture about demand paging. Demand paging is when an application accesses a page, it considers the page table, and if the page table, if a given page is not present in memory, it finds it from the disk and load it from the disk. This is the details of the demand paging. First, it makes an access to memory and finds that it generates page fault. And then if the page fault happens, then in the page fault, it scans the set of VM entries and check if a given memory access can be serviced by one of the object in the VM entry. And then if the operating system can satisfy the page fault, then it starts to allocate the memory, reading the disk block from the disk to memory, and update the page frame. So these are three steps. There are 3 remaining steps to service a given page fault. First, it has to allocate memory, and in the course of allocating memory, we are defining a new function, handle memory management MM fault. So it allocates a memory, and it load a given page from the disk to memory, and then it set up the page table using the install page function, and then it restarts the instruction. So this is big picture of demand paging, and we essentially covered all the concepts and details of method associated with demand paging implementation. Okay, so there are basically 3 things you are required to do. First one is page fault handling. So there is a function called page fault, and it is pretty much empty now, but you have to modify it so that the page fault can be handled properly. Page fault exists in Pintos to manage the page fault. So it is defined the exception.c, and Uh, Currently, it calls kill. So page fault function is currently empty, but now you are going to delete the code and then do the same thing. Um, First, you check if the given address access is valid or not. If it's valid, then go ahead and do and service the page fault. If it's not, you kill the process. And then next thing, you define the new page fault handler. I just named it as handle fault, but you may want to use the other name at your disposal. So handle fault. That is the heart of the function you're going to implement. So this is the page fault code. This is current Pintos code for page fault function. It calls kill f. So page fault, if the page fault occurs, then operating system kills the process. This is what's happening now. So you're going to delete this part, eliminate this part, and then replace it with the actual page fault management function. This is the control flow of page fault management. If a given address access is valid, then it searches the vim entry, it allocates the page table. It allocates the page frame, and then it reads the data from the disk to memory, and then it updates the page table with a newly allocated page. And we are going to abstractize it using the function handle fault. The next thing we have to do is to implement page fault handler. We name the function page fault handler as handle fault. So it is called to handle the page fault. When page fault occurs, it first allocates physical memory, and then it loads the file from the disk to physical memory, and you use the function load file. Then after we load the file, load the page from the disk to memory, we update the associated page table entry. And then in updating the page table entry, we use the function provided by Pintos, and the function name is install page. So what you are supposed to do is to write a function and fill in the function body of handle fault. So let's look at the details algorithm. For now, this is a page fault handler for loading the ELF file. So make sure that we're going to cover an anonymous page and the other fileback page installation. But for now, we are writing the page fault handler only for loading the ELF file. So in handle fault, we allocate the page and then check the virtual page type. And if it is binary file, then it reads the data block from the disk to memory and upsets the page table and goes success. If the page type is not binary and it's the swap or the other types of the file, then it goes to fail. The third part is load the file to physical memory. After physical memory allocation, you need to load the file from the disk to physical memory. So we write a function called load file. So it is passed with the address it needs to load the file, and then pointer to the virtual page object. So this is a function to load the page from the disk to physical memory. And you are required to implement a function to load a page to this kernel address. And the associated data block is specified by file and offset, and it is specified in the virtual entry. And actually, the function that actually reads the file is already there. So you're gonna use file read at or file read, and then you will use file seek to change the current location to read. And also, there's one more thing: the amount of data you are required to read may be less than 4 kilobytes. In that case, you fill the rest of the block with zeros. So don't forget. So this is a detailed step of load a file page to the physical memory. There is virtual page entry. This is virtual entry. And then there's page table, and then there's physical memory. So when you load the file, you search the location of the desired block from the disk using a file structure and offset. And then you identify the physical location of the data block you need to read. And from VM entry data structure, you're going to use offset field and file field to identify which file and which block you are required to read. And then after you identify the location of the disk block in the disk, then you read that block from the disk to physical memory, and the location of the physical memory you are required to read is specified by the page allocation algorithm you just called. So these are the functions you need to modify in this project. So there is page fault function, and there is load file, and then there's handle fault. Some of them you have to write it down from the scratch, or for page fault you have to modify it. And load file, you may want to write it from the beginning. In this part also you may want to write it from the beginning. And instead of modifying the existing file, you may want to create a new file, page.c, and put everything you have written to this C file. And then when running a test, 60-second timeout may be too short. So you may want to increase it to 120 or 180 seconds or something. Okay. There are many ways to modularize your code, but this is an example. So you may want to write a function that initialize hash table, and that initialize hash table and the allocate hash table. Also, you may want to write a function that scans the hash table and find the associated VME. And also you may want to write a function insert VME to the hash table and delete VME from the hash table. So these are the example way of writing your code or modularizing your code. And there are other functions like VM_hash and this one. And the first one is this is a function to calculate where to put the VM entry into the hash table. And this is the function to compare address values of two entered hash element, whether it's to check if it's the same or not. And this is the function that removes memory of VM entry. So this is the result of the checking. Okay, and there are a few more functions that needs some explanation, and I put a few more slides for your sake. First one is install page. So this one, it maps the physical page K page and virtual page U page. So it maps the page. It matches the existing virtual address page to the physical frame. The second function is about allocating and deallocating the physical page. First one is palloc get page, and the second one is palloc free page. Palloc get page allocate 4 kilobyte page, and it returns the physical address of the allocated page. And then palloc free page is a function that frees a given page and put it to the free memory pool. So these two are very important functions you're going to utilize in realizing this part of homework number 3. And there are two more functions. First one is malloc, and this is free. So malloc is a function that allocates a size of memory and returns a start address. And it is used to allocate the memory for dynamic objects such as VM entry. So this one you're going to use malloc to find a space or to allocate a space for VM entry, and free is the function that being used to release the memory space.